Okay, here we go into other indeterminate forms for L'Hopital. What? There's more than just 0 over 0, infinity over infinity? It's a whole bunch of them, actually. We've got forms infinity minus infinity. That's considered indeterminate. Infinity times 0, that's indeterminate. And then 1 to the infinity, infinity to the 0, and 0 to the 0 are all indeterminate forms. Now, depending on what the indeterminate form is, tells you what it is you need to do to get them into this form or that form to use L'Hopital. So if you're in one of these forms, well, you've got to manipulate the function or expression so that you can then get it into 0 over 0 or infinity over infinity to use L'Hopital. You can't go straight from this form to L'Hopital. So for instance, this is approximately, this is again a rough idea of why, 1 over 0 minus 1 over 0. To get it there, actually do the subtraction. 1 minus 1 is 0 over 0. So you would do the subtraction out, combine those fractions, and you would get yourself in the form where now we can use L'Hopital. Here, you'd have to make it so that infinity is actually the same as 1 over 0 times 0. We're going to do that here. And so that's 0 over 0. So we see how these are indeterminate forms. These are a little bit harder to see. But what they involve us doing is taking the ln and exponentiating e at the same time, because e to the ln undoes each other. Well, this would be e to the ln of 1 times infinity, and that's e to the infinity times 0. And infinity times 0 we know is indeterminate. Okay, same thing can be shown on these two pieces here, where we would do e to the ln, and we'd end up showing that we've got either 0 to the infinity or something funky that is of another indeterminate form. So I'm not going to do it with each of these, but anytime you've got an exponent indeterminate form, you're going to use this e to the ln trick. Okay, why did I show you this? Just to kind of show you that these are indeterminate, even though they might not look it. Like you might look at this and say, that should be 0. It's indeterminate. Here's why. So again, get everything in this form if it's in another indeterminate form, and we're going to do that in the next two examples. So the limit as x goes to infinity of x times sine of 2 over x. Okay, always start out with direct substitution. When we do that here, we end up with infinity, plugging it in, times the sine of 2 over infinity. Okay, well, 2 over infinity is essentially 0. So you've got infinity times sine of 0, yeah, which is 0. Because that's basically 0. Number over huge is 0. So, but here's the thing, that's not of either of these two forms. So how do we manipulate this to get it so it's 0 over 0, infinity over infinity? This is kind of complex, but a cool one. Now keep in mind, I see this in AB and BC calculus classes, but I've never seen one of these on the exam. And I see these certainly in college classes, in some, not all. Usually you're tested on these two, but why not show you everything? So we get the limit as x approaches infinity of. Now the sine of 2 over x, when we plug in infinity, goes to 0. We can divide this by 1 over x. Division by 1 over x is the same as multiplying by x, which is that. What that ends up doing, watch, is gives us still the same 0, because that's 2 over infinity, that's 0, over 1 over infinity. Oh, and that's the same as 0 over 0. So now we're in a form where we can use L'Hopital. So we got the limit as x goes to infinitar. And that right there is going to be the sine. Is it? No, it's going to be the derivative of sine, because we're using L'Hopital. We're ready to go because we got it in 0 over 0 form. So cosine of 2x, 2 over x, times the derivative of 2 over x, which is the same as 2x to the minus 1. The derivative of that is going to be times negative 2x to the minus 2, all over the derivative of this. That's just x to the minus 1. So that ends up being, well, negative x to the minus 2, or I guess I'll just leave it like that, right? Because that's going to be minus x to the negative 1, or just x to the negative 1. Its derivative ends up being this. Wait a second, they cancel. Isn't that beautiful? And so now we try to plug in the infinity, plug in infinity, and see if we get an indeterminate form and need to keep using L'Hopital, or if we're done. So we've got the limit as x goes to infinity. And so that's of cosine of 2 over infinity. Okay, well, let me just kind of neaten this up actually before we go on. That's 2 over x. And then I'll put the negative 2 out here. So we plug in infinity, you get negative 2 cosine of 2 over infinity. Well, 2 over infinity is 0. Cosine of 0 is 1 times negative 2. Negative 2. So again, this went to 0. We're doing cosine of 0. That's 1 times negative 2 is negative 2. Not bad. Not bad at all. So we're going to go over one more type of problem where we've got to do one of these manipulations. They're a little bit tougher. Remember, you know that you do not do more L'Hopital-ing, if you will, if you get to an answer that is determinate, right? That can be undefined as well. It just can't be one of the indeterminate forms. If it is, then you keep using L'Hopital until you no longer get that form. All right, this one's an interesting one. We'll plug in infinity, and we get infinity to the 2 over infinity, which is equal to infinity to the 2 over, well, to the 0. And that is an indeterminate form. You might be like, but anything to the 0 is 1. Not infinity. Not quite. Because what's happening here is this is growing really fast while this is growing fast, and they're kind of dueling it out. What does it end up on? So it might not equal 1. It might. Let's see. The first thing that we do is, and what I like to do, is I take the limit like normal, but we have to manipulate it so again that we get it in infinity over infinity or 0 over 0 form. So we've got this exponent we need to bring down. What I do is I exponentiate the whole limit, and at the same time I take the ln of x to the 2 over x. That ln and the e cancel out so that this expression is still equivalent to the original one. So what happens from there? I've got e, don't forget about that, to the limit as x goes to infinity of 2 over x comes out front. So that's going to be 2 over x ln of x. That's great. That's why we use that ln piece. Now let's kind of smush that together a little bit, and you'll see why in a second. Because if I were to plug in infinity here, I'd get 0 times ln of infinity is infinity. So I get the limit as x goes to infinity of 2 ln x all over x. Now, when we plug in infinity, because you can't really plug in infinity, we're going to get infinity, ln of infinity is infinity, over infinity. Sweet! Yes! What we now can do is use L'Hopital's rule because we're in one of the two indeterminate forms we needed. So I now use L'Hopital by taking the derivative of the numerator and denominator, and let's see where we end up. So the derivative of 2 ln x, don't forget, by the way, you've got that e down there. I dropped it. You've got that e we got to raise everything to. So derivative of 2 ln x is 2 times 1 over x. All over, the derivative of x is just, oh, sweet. It's just 1. Nice. And so now from here, what I've got is, I've got 2 times 1 over x. We're going to infinity. So that's going to be e to the, well, 2 over infinity. And as we go to infinity, 2 over infinity goes to 0, so I get e to the 0, which is equal to 1. So in this case, infinity to the 0 ended up being 1. It's not always. I got to be clear. You can't just say, oh, it's 1. That is not always the case. Very cool problems. I will see you all in the exercises for L'Hopital, but until then, be well, and as always, peace.